don't worry about the lab sheet today. So I just have a demo for you. Okay, so we take a look together. Okay, so this is a system for meshed filter. And if you look on the transmit side here, so we upsampling to 100 times. You can use 10, no problem. But then you need to change some other blocks uh, as well. And we also add the filters here. This is more like a transmit filter. Okay. So I think better to put the name like a transmit filter, or in a way is the baseband modulator. You can say it that way. Okay. And the reason we, oops, sorry. The reason we put a filter on the transmit side like this is so that we can change the types of pulses easier. Okay. So so here it just follows what we did before. Also, oops, I think this system is a bit error rate, but it doesn't have the meshed filter. Okay, so let me resave this file, and then I added the meshed filter in there. Okay. Okay. Actually, I don't even need the bit error rate here because I don't. I just want to show you the how do you call it? I just want to show you the shapes at the meshed filter output. Okay. Okay. So this is still the same, no change. Okay, because we always have this the comparator for decision. And this is the threshold decision that we saw. Okay. And I want to add a meshed filter here. Okay. Let me call this a meshed filter. And also because it's the on the receive side, let me change color to yellow so that we see it together. You can play with it together with me. Okay, no problem. Okay. So for bit one, we have one. We have 100 times. Let me see. Do I have the over square root 100? Okay. Yes. And then for bit one, okay, I use the same one because we match it. We match the impulse response of the meshed filter to the pulse of bit one. Okay. From here, then we can run the system and then try to see what the output looks like, especially after the mesh filter. Let me call it ZT. Okay, so that they are the same as we saw earlier. And then after meshed filter is Z. Okay. And then after decision is a hat. Okay. And okay, so let's run it and then take a look. Okay, we will focus a lot around here so that we can take a look. Here I put the SNR very, very large because I don't want to have so much noise in the system. Okay, so let's run the system and then see what the output looks like. Okay, then we can double click on the scope. Okay, the good thing about this is that oops, okay, something is not right. I don't, sorry. Also, I don't have ZT. Let me add one more here so we can see at the scope. Okay. Uh, so now we have 6 input to the scope. So let's add it to 7. No, so we can see together. Okay, and can I move this here? Okay. The good thing of labeling this line or the wires, so when you plot it, this labeling will appear on the plots as well. Okay. So this one is ZT, okay, or matched filter output. Let me call it matched filter output. That on the graph you can see very well. Okay, they are. I think you can move this thing to the line at the top. It's okay. Okay, let's run it and then take a look. Okay. Okay, so when I double plot, I see this. Okay, so let's take a look together. So this is for an RZL. Okay, this is the bit. This is the data bit. Then I do upsampling. Then I modulate this upsampling with the NRZL pulses. Okay, so I have a 0.1 and minus 0.1. They switch around. Okay, on the and then on the receive side, there's some noises. So you can see that there are noises related here. Okay. If on the receive side, I don't do match filter, I just do sampling, I will get the sampling of this value. One bit, I get one value out of it. So I get the values of like a 0.1 and minus 0.1 at the output of the sampling. Okay. But when I do meshed filter, what happens is because meshed filter is like a collection of energy. So I have like the peaks, sum of the energy of the whole bits. So I have the peaks at minus 1 and 1. Okay. Switch around. Okay. And when we do the sampling, we sampling at each second. So we sampling at the negative peak or the positive peak, especially, etc. And then we make decision of what we have. So basically we have 1 bit delay because of the filter. And then we have, minus 1, 1, oh, minus, then we make, then we have, after sampling, we have minus 1, 1, minus 1, 1. So it's the same thing as the data, right? Same signs of the data. And same sign as the M that we transmit. And then when we make decision from this to this, okay, we have a hat. This is a hat with 1 bit delay. So we don't count the first bit. So we have 0, 1, 0, 1, 0, 1, 0, 1. So they are the same. Okay. If I add noises, so let's say that I add more noises. So let's do 10 decibels instead. And then I run the whole system again. Okay. So what do I have? So this is what I have. Okay. So instead of looking at the mesh filter output, that looks very, if you look at the receive signal now, they look very bad, right? They look like, I don't know, very noisy. But mesh filter is a collection energy for each bit. So you can still see very nice the curve like this. Okay. But now you don't see like the very uh, uh, smooth output from meshed filter like on the previous simulation. In this case, we use very low SNR, but they still have some shape, right? After the A to D or sampling, then you get whatever value you're sampling in each second. Okay. So because of the noisiness, you don't have the 1, 0, 1, something like 1 minus 1 minus 1, exactly because of the noise level. And anyway, so and then after you make decision, this is what you get: 1 0 0 0 1 1 0 0, which is the same. Okay. So mesh filter, it collects energy, so it helps you a lot. Okay. If you don't use mesh filter, imagine you just do a sampling on R at each second. You even get bad values, you don't know, maybe you get some errors and so on. Okay. So in this system, you can add the bit error rate counter, but make sure you don't count the first bit on the receive side. Otherwise, you will, sort of like shift around everything. All right. So you don't count the first bit at the decision, and then from there, then you can count the error rate, and you should get some curves like what we talked about earlier today. Okay. So for these, the Simulink, you have any question? Everyone, Pyo, Sananpat, Thirarat, you have any question? I just added here, just one little block, and this is called a meshed filter. Okay. In fact, if you don't if you don't do meshed filter, if you don't assign the coefficients to match the powers of bit one, if you just do like some other, you can change this to low pass filter. If they don't match, then they become low pass filter. You can try that as well. Okay, so let me open another file. This one is for correlators. For correlator is it has more blocks in here. So let me take a look. This is the line code. And you can download this file from Google Class. And I built it based on Simulink as well. And it's a bit more difficult. Okay. But so let me take out this block. There's no need. Okay. So first, let me start from very high SNR as well. Okay. So everything here is almost the same actually. Here is the same. Okay. But then the correlators consist of these two blocks. Let me change color so that it's not confusing. Okay. Let me change the background color to maybe let's do magenta. Okay. Yes. So we know that these are for the receive side, especially the correlators. Okay. So this is the system for correlators. Uh, the correlator circuit consists of actually just two blocks in general. One block is a multiplication here. So when you have the receive signal here, when you have the receive signal, correlators consist of these two blocks. One is multiplication of the receive signal with the powers of bit 1. This is for NRZL, no? You can multiply with the powers of bit 0, but at the decision, you have to switch how you make decision. You can do either way. Okay. So on the left here, all I do was I just built a powers of bit 1 similar to this, but separately. Okay. Just for one bit. Then I multiply with RT, and what follows from the multiplication is the integration. Okay. This one is an integrators. What did I do here? I think I didn't do anything much. I just put sampling time as 1/100. That's all, I think. And also, I need to reset the integration with a reset clock. Okay. And the reset clock is 1 period. So these two, there's reset like this because we integrate just one bit and then we throw away the values. meaning that we reset the values, we reset the integrators at every bit time. You know what I mean? We integrate and then we don't count, we don't integrate 1 bit, 2 bits, 3 bit and sum together. We integrate just the region of 1 bit only, and then we reset the clock. Okay, and then followed by A to D and then decision, and so on. So if I change the multiplication pulse here with the bit 0 instead of bit 1, then here I have to switch from from greater than or equal to 0 to less than or equal to 0. Okay. So, and if you take a look here, I also add something here, which is a delay. This is so that when you do the A to D, you get the correct values anyway. So you can try to play with this plot. So let's take a look here and let me try to show what you get. Okay. So let me run. Oh, let me do this SNR very large first. Let's do 50 decibels as before. And I run only for 10 bits, just for demo. Okay. You can ask question if you have any question. Okay. And that's it. So it just run. Oh, sorry. This is an old file. Okay. Where's the other file? Oh, here. Oops. Okay. So let's run this file. This is for correlators, and I run, let's say run 20, okay, 20 bits. And at the bottom, it keeps running and so on. Okay, that's it. Yeah, this is what we have. So let's take a look at what we see here together. Okay. So these three are the same. Or on the left hand side, they're always the same, right? Uh-huh. And then, what is this? This is a repeat of the plot. Let me take a look. After R, what do we have? So we plot here. This is after multiplication. And then, so let's focus at the output of the correlators, which is what we want. Okay. Okay. So after the received signal, we multiply with the bit 1. So all we get is just the same shape because bit 1 is just a positive amplitude, right? But if you take a look at the amplitude here, is the below is divided by 10 here. Okay. Oh, why is it divided by 10? That's strange. I see, because I multiply with the same thing, right? Okay. So that's why it's 0.1 multiplied with 0.1 becomes 0.01 here. You can zoom on your screen, no? And then I do this, okay? I integrate each bit. So that's all I do. I integrate, from left to right. So I have increased value all the way to the top, okay? And then I reset the integrators. So for the next bit, I also integrate from left to right. So I have from 0 to minus of the area, no? For here, I also do the same. Here, there are many bit ones, actually. So these are all ones. When I integrate, I do it 1 bit at a time. And then after the 1 bit, I start again, and again, okay? So the shape may look a little bit different from meshed filter because this is through integration. Then for negative, also here there are 3 bits. So we integrate 3 times, okay? And we just keep doing this. And then we output the maximum value, or in a sense, it's just sampling at the peak. So this is what we have, okay? Okay. So if the system can output the maximum value, then you don't need A to D. But in Simulink, because it's continuous, no? So I just sampling. Okay, so this is what we get. And then we make decision. If it's positive, we get 1. If it's negative, we get 0. So we get 1, 0, 1, 1, 1, same thing. Okay. Here we have an extra bit. We don't count this bit when we do the error correction, error counting. Okay. So so please focus on the output at the mesh filter and output at the correlators. These are the two different things, and they look different. But we get the same value at the peak here in both system, because both system they are equivalent. Okay. Any question here? That's all I want to show you about the how do you call it? Uh, the simulation. You can play it at home. There's no need to send anything today. Okay. In fact, if you change the, if you in either system, you can change the modulation scheme by changing the coefficient on the transmit side. Okay. Here the green color is a transmit filter. Change whatever you want. Okay. Let's say I do what do you call it? Let's say I do uh, unipolar NRZ, for example. Maybe I cannot do it here because this is the, if I do unipolar, I have to connect these directly. I have to take this out, no, because this changed from positive to negative. So let me do Manchester. Okay. For Manchester, we have half positive and half negative, right? Let's do half negative followed by half positive. So that's all I do. Okay. And on the receive side, because this is on the receive side, we multiply, no, for correlators. So I multiply with the same thing. So here, if I run the system, then I will uh, have different pulses than before. Okay, so let's run the simulation. It takes a little bit of time. There's no need to do 100. We can do 10. So it's faster. Oops. Yeah. So this is what we have. Okay. So if you take a look, see for bit one, each block here, each grid, there are 2 bits. So 1 1, right? So we have half is negative, half positive, half negative, half positive. Okay. And here the same thing. And then we multiply, and then we do the integration. So this is what we have. So okay. uh, Something is, one moment. I think I should get something different from here, but it makes the right decision. Oh, that's strange. Let's take a look. I multiply correctly. So this is for half negative, half positive, right? Okay. This is also half negative, half positive. Okay. I see. So basically, I just get all ones, I think. Is it all one? No. We should get half. We should get ones, and then we should get positive and negative. You know, alternately. Okay. Difficult to see. Let me do 10 bits so that it's a bit easier to see. Okay. Still, something is wrong. Click, click, click. I think the output is not right. Something is wrong here. So plus and minus, plus and minus. No, the output is not right yet. Let me check what's wrong. So half negative, half positive. Okay. Half negative, half positive. Reset clock 1 second. Okay. And we integrate every 1 second. So this okay. Let's see. The output from here to here, they look okay. Here is okay, but here looks strange when we multiply. Why do we have a very strange? Can I zoom inside? I want to zoom and see what happens. I think we should have something different. I see. Wait. I see. Something, I did something wrong. Okay. Because it's like this. If I take a look at the slides, and now I know why. Okay. If you remember when we look at the meshed filter, uh, because here we reduce to one single correlators, right? Yeah, let's go back to this lecture a little bit. So we try to convert, oops. In Simulink, we can use this system with two correlators. But because I use only one correlators, I need to subtract one pulse from the other pulse, right? Then let me show you here. So this is what we need to multiply with the received signal, right? For, if you go to the next page, for NRZL, this is what we get NRZL, okay? And for NRZL, we can subtract S1 from S2 or from S2 from S1. So for NRZL, we do this. We do bit 1 minus bit 0. Okay. So I have 0.1 and then minus 0.1. So when I subtract together, I get, how do you call it? I get minus 0.2. Okay. Oh, 1 minus become plus. Sorry. I just want to say that that's why we multiply with just the pulse of bit 1 in the mesh filter and correlators. So we just get this 0.2, right? And we use this to multiply in correlators or in the meshed filter. But then when we do Manchester, okay, if bit 1 is like this, half negative, half positive, this is like 1 second. And minus bit 0, which is half positive, half negative, is bit 1, this is bit 0. What do we get? Okay, in the Simulink earlier, I just used this to multiply, no? And it's not correct, okay? So if I set 1 and 0, then I subtract these from together. So half the bit, I have negative minus positive. So I have negative. Okay, so, and then here positive minus, so it's the same thing, right? Okay, so what's wrong? So this is the shape of bit 1, right? All right. Minus positive, positive minus negative. So I have this A. So it's actually actually correct. me see. So what's wrong here? I don't know. Why does it look so strange? Hmm. Actually, what we should get here is like for negative bit, we have negative values. For positive, right? Yeah, yeah. Then for positive, we get one, all positive. When we have negative, we have bit zero, we have all negative amplitude. So when you do integration, it's very, very direct. But what did I do wrong here? One moment, let me take a look. Maybe let me plot this thing. I start to get confused here. Let me take, uh, let me add one more port in the scope and see why did I go wrong. Let me add one more. Let me add one more port for what I used to multiply, no? So let me do this here. Okay. Did I multiply the right thing? What did I do? So now I will focus on the last plot in the scope and see if I multiply with the right thing or not. The coefficients are the same, right? Negative and positive. Oh, this one is just copy, right? Negative and then followed by positive. Hmm. Okay, so let's take a look at the last plot in here. Here. Hey, wait. So I have 9 plots, right? 8 and 9. Okay, okay. Oh, this is the 9 one. Okay. Why does it look so strange? Hmm. Ah, I see, I see. Maybe because here I I already have sampling time of 1 over 100. So when I increase more, so it looks very strange. That's why. It's like oversampling 2 times, I think. I think that's why it looks very strange. Eh, hmm? So let me try one more time. Ah, finally. Finally. I think what I did earlier was that, okay, so now I can take out this. I'll leave this scope on again, okay? I think what I did earlier was, normally when we have this bit that we transmit here, the sample time is 1 only, right? And then I will oversampling with 100 later, no? But here what I did was I put in number 1 and then I put oversampling time already 100 times. So I did it twice, just too many, no? So if I set sampling time here as 1 over 100, I can do it here, but I have to remove this, okay? Okay, so I think that's the reason. So now it looks okay. If I take a look at the plots, so we can take a look together, okay? So this is the receive signal, and all I did was I multiplied the receive signal with bit 1 forever, okay? So whenever you have bit 1 here, you multiply with the same thing, you get positive. Whenever you have bit 0, you multiply the Manchester for bit 0 with bit 1, you get negative. So that's why we have constant value. And then for correlators, they just integrate like for every bit, do the same thing again, okay? And then sampling, okay? So you see that this is the same as what we transmit, but with one delay bit, okay? Okay, sorry for a little bit of confusion. You have any question? I hope you understand what I was trying to say because I had some error, so I had to try to solve it. Okay. Any question from you? No? I know on the computer it's a little bit hard to focus on the screen all the time, but still, no question at all. Okay, so no question. You can try to play with it and try to review the lab well. Okay, you may have to run it during exam time and so on. Okay, I think that's all from me today. Yeah, I think it takes longer than I thought again. So I'm gonna stop presenting and stop the recording. Okay, Tirarat, you have any questions? Mhm. Oh, sorry. Okay. No, I cannot hear you. Okay. Any question from you, Tirarat? I don't know why I cannot hear you for some reason.